Thanks, Graham. Can you hear me all right? Yeah, it sounds pretty loud, doesn't it? All right. So what I'm going to talk to you all today, first thank you all for coming, and it's a little warm in here, so I'll try not to put you to sleep, is to talk about sustainable and resilient cities. And the term big data, have you all heard that here? Everybody's hyped about big data, so we have to use it. Yeah. But basically thinking about how you can use data and information in new ways to improve human and ecosystem well-being in cities is what we're focusing on here. So thinking about the challenges with cities in terms of sustainability and resilience, here is Superstorm Sandy. Maybe I'll try this mouse, and then you'll be on both screens, which hit New York City. This is some of the roads in New York City during that storm, shut down the entire city. The transportation systems were flooded out, all kinds of problems there. So we see these major events happening and cities just failing. So clearly lacking a whole lot of resilience to stand up to these sorts of events. Then on the sustainability side, we have massive poverty varying in different countries. These are urban slums in India, so they're trying to figure out what to do about those. We see more and more urbanization across the world. People are moving more and more to cities, causing increasing stress on natural resources and ecosystems, the poverty and health problems, exposure to natural and human extreme events. And a lot of times these problems are overlapping and interacting systems that we're sort of thinking about separately, but in fact they interact with each other. So it's systems of systems problems. And how do we think about, sort of expand our view and try to understand how these larger scale interacting systems of systems behave? So we're getting more and more information that we can bring to bear to these kinds of problems and try to understand these interactions. So this is the big data stream where we have a rapidly changing world. We're trying to figure out what to do as best we can with limited information, but what can we do more with the information we have? So this is the framework that we've been working on for a number of years now, where you have all different kinds of sensors, everything from cell phones to satellites to instruments being put out in the environment. All that information can be harvested and brought together, sometimes from multiple different sensors. Then you have to do data fusion or integration, and you can create data products or services that then provide the information you need to feed into models, visualizations, and decision dashboards that might sit on the web and be easy for people to understand, even if they have some very sophisticated tools underneath, and enable folks to make information-based decisions, taking advantage of all this information, including archives of information that are out there in all sorts of places. So we're trying to put together both the cyber infrastructure that allows this, as well as some of the algorithms that are needed both to create the data services and the modeling services and the decision support services that are delivered across the web with these tools running in the cloud. And this is a partnership with the National Center for Supercomputing Applications, where I'm a faculty affiliate, and I work quite closely with them on the technology aspects of this. Is this a little bit echoey on the sound? Maybe if I moved it down a little bit, it might be better. Is that better? Okay, a little too close. So the focus of my work that I'll be showing you here, I have various different applications that are taking advantage of some of the same technologies, but here we're going to take a look at urban stormwater problems. So in urban areas, we see more and more impervious surfaces where we've got water running off very fast off the cities, and it's causing more flooding, sewer overflows, and ecosystem damage. So we also see that stormwater is a valuable water source, especially in areas that don't have a lot of water, and that's one of the things why we're here, is to see what Australia's been doing in terms of harvesting stormwater and You're doing a whole lot more than we are in the US, so it's been really fascinating. In the US, there are about 860 billion gallons of untreated wastewater and stormwater that are released to the waterways every year. And this is Lake Michigan right here. And you can see some poor boat trying to sail on Lake Michigan with this brown plume coming out because of untreated wastewater that was released during a major storm. So we've been working closely with the Metropolitan Water Reclamation District of Greater Chicago, or MWRD, I'll call them. MWRD covers, this is the city of Chicago right here. Oh, and I gotta remember not to use that pointer, use this one so you can see it on both screens. This is downtown Chicago. This is Lake Michigan right here where they're releasing, during major storms, they release out to the lake. Most of the time they release into these waterways and it goes down the Illinois River and eventually winds up in the Gulf of Mexico where it contributes to hypoxia, where they don't have enough oxygen. So Chicago's idea was they were going to put these massive deep tunnels under the city. They put them under all the waterways, so every waterway has a deep tunnel under them. That's what these lines show. It's both the waterways and the deep tunnel systems. 109 miles of tunnels. I'm not going to try and convert that to metric for you, but it's a lot. Up to 35 feet in diameter, so that's what, maybe 10, 12 meters. You can see this guy here, how large this tunnel is, to try to capture these sewer overflows. So a combined sewer is where you have both the wastewater and the stormwater are in the same pipe, captured in the same system. So when a big storm comes through, it can't handle all the water, and it winds up having to discharge some of it untreated. These are older systems, very common in the US and in older cities, in the center city areas. This is called gray stormwater infrastructure, where they're putting in these big tunnels. And every one of these dots on this map, if you can see them, those are sewer overflow points. And these are the sewer sheds, which are the areas that drain into those sewer overflow points. And the red areas are the overflow points that we found were frequently overflowing, or they were either doing it a lot, or they were having very long discharges compared to the other points. And the MWRD didn't actually really know that at all, that there were certain areas where there were a lot of problems. So we honed in initially on this area where there's a lot of these high-risk outfalls, a lot of this raw sewage being released. There's 300 of these CSO points in the whole system. So the first part of the work that I'm going to show you, keep going a little bit lower, try it again, is my student who just finished her PhD, and she's been developing a model predictive control. Yeah, turn the volume down a bit, that might help. Okay, thanks. Try that. So this is what's called model predictive control, which is where you have, try it again. You have a moving window, so we're going to forecast the next 2 hours. What do we think is going to happen in this deep tunnel system? And then, given that forecast, we'll decide what to do in the next 15 minutes. We'll implement that, and then we'll forecast out another 2 hours, and then implement 15 minutes again. So we start out with a precipitation forecast for those 2 hours. We create what's called a population of control strategies. How many of you are familiar with genetic algorithms? Fair number of you. Okay, great. So in a genetic algorithm, you're creating a bunch of possible strategies in a population. It's meant to mimic natural selection. And then those members of the population compete against each other, and over time the population gets stronger and stronger. But you have to tell it, what is a strong population? What do I consider to be good fitness for these? And in this particular case, we're using a hydraulic model of this whole deep tunnel system, and our good fitness says we want to minimize how much overflow we have going out to these stream flow systems. And we want to meet pressurization constraints. The problem is when you have these tunnels, When the water flows in very quickly, they can pressurize, and you can actually have manhole covers. When they first started operating this thing, manhole covers blowing right off the top, and cars being thrown around up on the street. So they're very careful now to try not to pressurize the system, and so we have a constraint on that. What the operators have control over is some gates that they can move, and I'll show you those in a moment, and pumping rates in the treatment plant. So how much of this water are we going to pump out of this tunnel and treat? And then, so we continue that process and we keep moving ahead until the storm is over. So here you can see the different pieces of the system. We started out with a pilot scale with and I have a hard time going back and forth between pointing with this one and changing the slides with that one. So I'm going to give up on that. Here's our sewer sheds. There's only 4 of them. So this is those areas I showed you on the map that drained into the same inlet. And then we have these, let's see, this is the interceptors, which is the first pipe that the water hits when it comes off the sewer shed. And when there's not that much water, all the water will flow down this way and into the wastewater treatment plant. It'll be treated, and then the rest will be discharged into the waterway. If the flows get too high, then you have a weir where the water flows over and it goes into the deep tunnel system, which is this thing. And there's a sluice gate. And if the deep tunnel gets too full, then they shut that sluice gate. And so their current operating strategy is when the water levels get up to 70% of the pipe diameter, then they shut them all at once. And once they shut that deep tunnel off, any overflows then go straight down here into the water and discharged untreated. So this was the very simple, so we have 3 different gate locations. These are our GA, it's called a chromosome with our different decision variables. So what's going to be the sluice gate position in the first spot? It's going to be open or closed in every 15-minute period. And then this is the second sluice gate position, the third sluice gate position, and then the number of pumps that are online at this wastewater treatment plant, which pump out of the tunnel. And each one of these, interval 1, 2, and 3, that's those 15-minute intervals. So you have the same 4 variables that you're deciding. And this is done with a real-coded genetic algorithm, which means a basic genetic algorithm, everything is coded as 0s or 1s, but these are coded as real numbers. And now I've shifted ahead. We looked at a bunch of, the problem is when you're trying to solve this problem in 15 minutes to make a decision, you have to be able to solve it pretty quickly. And when we're using the hydraulic models, they take a long time to solve, and we have to run them over and over again. So we came up with some different approaches for trying to speed up the genetic algorithm and get an answer faster. The first one is called the shifted genes approach, and what that does is, here's my 4 intervals. So I've solved this one for the 2-hour period, 4 15-minute intervals, and I've implemented the first 15-minute solution. The rest I haven't yet implemented, and instead of starting the next period by reinitializing randomly, which is what you typically do when you start a genetic algorithm, I take those best solutions and just ship them over here to be the starting solutions for the next optimization. And then the last period is randomly set in the usual way. So it saves some time, gets some good solutions in there to start things off. The second approach is a couple different ways of reducing the search space, where, so one approach to that is to say, we're not going to consider these gate positions right now, so the sluice gate can slide up and down, but if it's above the level of the water flow, there's no point in looking at that. The other way you can do it is by just allowing fewer gate positions to be considered and having a more coarser kind of discretization of our decision variables initially, and then we shift to a finer discretization later. And then another approach uses a microgenetic algorithm, which is where you have small populations that evolve through 40 generations, and each generation has 10 subgenerations. So they're very fast, and then we take the 6 best solutions and we restart with a new population. There's another approach that isn't here, which is called a compact genetic algorithm. And so this is the performance of the different approaches. The base comparison was with a population size of 272, so this was a basic genetic algorithm. We have some theory about how to do the parameters for a genetic algorithm, which we used to come up with that population size of solutions that we started with. And then all these other approaches, we compared how quickly did I get the answer relative to that, and then how well did I do in terms of how close was the optimal solution to what I had with this full, very computationally intensive approach. And then how did I do on my constraints? Remember those pressurization constraints with the other approaches. So I want to make sure that I'm not getting pressurization. So these approaches over here were faster, but we didn't do as well here with the compact genetic algorithm in terms of the optimal solution. We got higher overflows and more pressurization. So this approach didn't work too well. The micro-GA had some issues here with not meeting the pressurization constraint, although it was the next faster. So the best approaches were actually these different ways of reducing the discretization and kind of coarsening the approach initially and then switching over to a finer discretization on our decision variables. And that turned out to be the best approach. This actually lines up with some findings. They were kind of different ways we did this on a completely different application for groundwater remediation monitoring. So it looks like this sort of approach is holding up fairly well, at least across 2 different applications. But we have to try it out on others. In terms of how much overflows we could reduce by optimizing, the baseline that we used the operator shut when the tunnel is 70% full, but they thought, maybe it'd be okay to go to 80%. We're fairly conservative. We might be able to go to 80%. So we looked at what would happen if we actually optimized and we allowed going as high as 80%, but you may not go that high. And in that case, we got a 13% decrease in overflows. These patterns are the CSO levels in each of the 15-minute intervals. And then this is how much flow was pumped out at the treatment plant. So we see the patterns are fairly similar in these two. We're not seeing huge changes when we optimize. And that's because when these big storms come in, there's not a lot of extra room in the tunnels for us to play around with. They fill up pretty fast. The last one, though, shows us if we took away that pressurization constraint completely, we see drastic changes, 77% reduction in overflows. And these are different overflow points. So those are our 3 decision variables on, and the pumping station. So we're still seeing some overflows at the pumping station, but the other locations we're not seeing any here. So there is capacity there if we were willing to risk pressurizing more. And what will be interesting is they're actually creating reservoirs to hold some of the storage. So when those reservoirs come online, they've been building this whole system since 1979. It takes a huge amount of time to build this. When those come online and they have more capacity, we may see some pretty significant reductions in these overflows. And that's something we're going to have to model again in the future. So that was the pilot scale. The purpose of that was really to identify the best genetic algorithm approach and see how well we did. And then we started to look at, well, what happens when we scale this up? So here's the pilot scale that we looked at before with those 3 overflow points and our treatment plant here. Turns out these 3 overflow points only represent 7% of the flows coming into that treatment plant during this storm that we're working with here. So we expanded it first to look at this area in red. where there's 20% of the treatment plant inflow coming in. And in each of these, we just left these gates fully open and didn't optimize them at all. So in terms of the simulation that was done. Then we expanded and looked at this whole area here of the system, quite a bit larger, which was 45% of the treatment plant inflow. There's still half the flow that we're not modeling at this point, but we were starting to get pretty significant computational loads. When we looked at this large-scale system, then we said, well, what would happen? There seemed to be certain pinch points in the system where the flow was not getting into the tunnel very quickly and it was backing up locally at certain points. So what would happen if we put in some larger diameter pipes there? And so now we added an outer optimization loop where we said, we said, let's allow some of these pipes to have a larger diameter, and that's the outer piece. Choose the diameter of the pipes, and then the inner piece is determine how you're going to operate the system once you have that pipe installed. So the inner optimization loop is what we were doing before, but we've added an outer one to change the pipe diameter, and we wanted to see whether it was worthwhile to do that. So it turns out that it's not. We looked at a range of different costs of the electricity coming in, comparing low electricity costs to high electricity costs that we might see in the summer. And how much are you charging for the CSO? So they have to pay a penalty when they have a CSO, and ranging that from $1 per cubic feet per second, which is what they have to pay now, to $10 if it were a higher rate. And how much is the excavation cost? And my student looked up numbers for excavation. And then she looked at different frequency storms, so smaller storms that might occur every year, every 2 years, and every 5 years. And how many years, given these different costs, would it take to pay back the investment of putting in these larger pipes? And it turns out when the CSO cost is low and the electricity cost is low for the pumping that we do, the years to pay back is quite long. When they're high, they're shorter, but they're still fairly long. And especially when you look at these 5-year storms that have pretty low probabilities. So we have to look at this in a little more depth with a sequence of storms, probably along a longer period that might represent the kinds of storms we might encounter in reality rather than these artificial storms. But it looks like we might need to turn to something else. So this is where we're starting to look at green stormwater infrastructure. So MWRD is being sued because they have too many overflows and the water quality is not good. And they're, as part of the consent decree, they're being told you need to put in green infrastructure. So green infrastructure, I think you call it water-sensitive design here, or low-impact development. Might be green roofs, might be bioswales, might be permeable pavements, all kinds of different approaches. When you're talking about things that involve putting green spaces in, then you have all kinds of co-benefits that come with that. You get habitat, you get possibly energy production. No, that would be energy savings, because if you're putting in trees, then it's cooler. So you save some energy from that. Community can play in the green spaces and exercise. The air quality can get better. So there's a lot of co-benefits there, and typically when stormwater engineers are designing these things, they just design them to capture a certain amount of stormwater, and they don't really consider all these co-benefits. But if you design them well, then you can do a much better job of designing them in a way that both people and ecosystems will benefit from. So this is a new project we have from the National Science Foundation to look at creating a new design framework that considers more of these co-benefits. And we're calling it crowdsourced green infrastructure design, because if you're going to put green spaces in people's neighborhoods, they're going to have something to say about that, and they might not like them. So sometimes you hear complaints that they're weedy and ugly, and people might not want them in their neighborhoods. So to have people involved in how you design them, and what's this green space going to be like, and what benefits will you get from it, to design it in a way that they will like. So we're using some of the cyber infrastructure that I mentioned to do that. So we'll have models of the green infrastructure impacts that'll look at human, hydrologic, and ecosystem impacts of these green spaces. Geospatial tools that'll feed the data into the models. This all gets implemented in a workflow system, which is the cyber infrastructure, so that the sequences of steps that you might do to estimate impacts, which might involve running 4 different models and going to 20 different data sources, will all be automated in sequences and saved as a workflow that can be shared from one researcher to another. And then that can be published to run as a web service and as a web application interface through your web browser. So you have very sophisticated tools running behind the scenes of a very simple web browser where stakeholders can look at potential designs, they can create them themselves, they can modify them, they can also tell us about errors that we might have made in our models where maybe we don't know some of the details about what's going on in their neighborhood. They could see what our assumptions are and tell us where we need to make some changes. And they can rate the designs. And so part of the research will be figuring out how to aggregate that information and then use it to help come up with better strategies that incorporate those stakeholder views and to do that interactively. Then the researchers will also be using this to observe this stakeholder process and see how well do people do using these kinds of tools, what kind of designs work better, and how can we best calibrate and validate our models given this information we're getting from people, and then be able to link new models and tools more easily when everything's set up in these workflows where we can pop different components in and out. So in terms of thinking about the green stormwater infrastructure impacts that they have, we have 3 facets. One is the hydrologic modeling. The third is the economic evaluation. Did I say second is the economic evaluation? That'll just be a simple cost. We'll have an environmental ranking that will combine watershed scale modeling with a site scale model that has much more detail about the hydrology of what's going on. So the site scale model is called RESIS. It was developed by Larry Band at the University of North Carolina, Chapel Hill. It's a distributed type model with a lot of detail about what's going on in terms of the biogeochemistry as well as the hydrology. SWIM model is more of an industry standard for looking at watershed scale, large scale. And we're also going to bring in IUHM, which is the Illinois Urban Hydrology Model, that looks kind of stochastically at where does water flow within an urban environment, because we don't necessarily know the details even of where the sewer system is and exactly where water will go. So we're going to put those together. That'll give us an environmental ranking. Down the road, we want to bring in some of the water quality aspects to that as well, but this is where we're going to start. On the human side, in terms of the impacts on humans, we're currently focusing on human preferences. And I'll tell you a little bit more about how that's done in a moment, but there's a social ranking that will come out of this. So why human preferences? Well, it turns out that green spaces can significantly affect people's health. And they've done studies. I have a colleague that I'm working with on this work. He's worked in a high school where they randomly assigned students to 3 classrooms. One had a window with a view of a wall, one had a window with a view of a tree, and one had no windows at all. And the students in the room with the tree as their view had better performance when they were asked to, do kind of stressful activities. They were able to do better than the ones who had no window. So green spaces have a dramatic effect on people's health and how they recover from stress that they can actually measure physiologically. And it turns out that if people like the green space, they like the way it looks, then they get better health benefits from being around that green space. So we can use their preferences as a metric for what effect is this going to have on their health. But currently, there aren't any design tools to help people who are designing these kinds of green spaces understand what effect it might have on people, other than to try to come up with a design and show it to them and then see how well they like it. But we want to be able to sort through a whole bunch of possible designs, try to come up with some that look like good possibilities, and then show them some good possibilities and not waste their time with things that they hate. So my colleague has created a data set where he takes a particular setting. So this is Galesburg, Illinois, Main Street. This is what it currently looks like. He adds trees to it, just doctors up the photo. And he adds different configurations of trees and how dense the tree cover is, and then asks people how well they like it. And they also measure physiologically. If we're showing you a scary movie, and then we show you this green space image, how quickly does your heart rate drop from having seen the scary movie is actually dependent on the green space and how well you like it. So we're capturing that effect with this preference model, which we are training using image mining to take these images that people like and try to pull out what are the features that people like, and then predict how well people will like a new green space image. And we're using information from Kaplan and Kaplan. They have a human preference matrix for what people like about green spaces. And turns out people like coherence. So we have, from sort of ancient times, green spaces can be scary, right? If you're going out in the forest and it's very dense, you could get lost, you could get eaten by a bear. And so we have this sort of primal response to green spaces that don't look manicured and don't have some human control over them, that those are scary places where we don't want to go. Because of that, we like a little coherence to our green spaces. We want to be able to identify shapes and their layouts. We want some legibility where we can see trees and pathways that show that somebody's managing this green space so it's safe. Also, some complexity. We don't like when it's too uniform. So some amount of openness, but also some closeness in there. And then some mystery, where there might be a path that goes off, but it's hidden by a tree as to where that path goes. We're intrigued by those kinds of mystery, and we want to go explore them. So people like those kinds of features. So for each one of those, we have an image mining technique that is capturing that aspect of these green space designs. And then we use that to train a machine learning model that takes the images, extracts those different features, and then uses a k-nearest neighbors and adaptive boosting approach to predict what the human preference rating will be, where 1 is the worst, they don't like it at all, and 5 is the best, they love it. So we did this in Galesburg. This was the pilot work that we did before the project was funded. So now we got to go back and explore this some more. But on our training set, we were able to predict how well people would like them with 96% accuracy, so that was pretty good. But on these models, you really have to have a validation set that you didn't train on. And because it's a fairly small data set and people are a little bit fickle and not totally consistent in their ratings of green spaces, the validation set was 74%. And I wasn't too happy with that, but my colleague who created the image sets, he was really excited because he said, if you can predict how well people like a green space with 74% accuracy, that's actually really good. So now we're working with a larger data set, and we're going to come back and see if we can do any better with that data set or not. But here's an example of what it might look like. So we've applied this in Baltimore, and we have a neighborhood where here's the existing neighborhood. The preference rating is 2, pretty low. People don't really like it. We add some more trees, and we get a rating of 5. So that's how the process works. And then we're looking at what's the benefit of adding these trees. So if people like it much better, we see a pretty strong social plus associated with adding the trees, but we've also got to look at the hydrology. So here we're using that rhesus model and comparing. Here's the existing development. The modeled annual mean stream flow for this watershed is here. We estimated what the pre-development flow would have been before they put in all the houses, and it was quite a bit lower. If we put in one tree, we see that the stream flow drops a lot. So we see a lot of benefit. This is one tree for every yard in this particular neighborhood. If we put in 2 trees, though, benefit starts to drop off. With the groundwater flow, here's the existing, here's the pre-development. 1 tree brings us up closer to what we had pre-development. 2 trees, we don't see a lot of incremental benefit. So we think, based on these results, if we go back here, 1 tree per yard is going to do us pretty well. This is not even 1 tree per yard here, and gets us some significant hydrologic impacts. So this is the kind of thing that we're trying to do. Turns out there's a bunch of other co-benefits as well, and there's some folks here who have been doing some nice modeling of some of those efforts. So we may try to bring in some of those models as well and look at things like heat island effects and other benefits from this sort of green space. So our next steps, we're collecting more training images, talking about hooking people up and then having them walk through a city and measure what kind of green space they've encountered, and then see what effect that has on them. So they would be instrumented to see the physiological response from seeing those green spaces. Improving the predictions of ecosystem and human health impacts, doing some validation. We're going to be looking at Baltimore and Chicago initially, and then we want to branch out to other cities and hoping we can try this out in Australia as well. The design interface, we'll be designing as this cyber infrastructure as well as the interactive optimization, working with some stakeholder groups in Baltimore and Chicago to try this out and see how well they like it, and see what it does in terms of bringing people to consensus around designs that they might like better. And then the last piece is looking at green versus gray infrastructure trade-offs for the Metropolitan Water Reclamation District. Should they put in more big pipes, or should they put in more of these green spaces, and where should they put them? Then we're leveraging some national activities in the U.S. that are going on. We have a working group that's working with stakeholders in 5 U.S. cities, and that's sponsored by NSF. And then we have a task committee that's also creating a position paper looking at performance-based infrastructure. How do you measure how well you're doing on this kind of infrastructure? And we're focusing on stormwater design. Then the last bit I have is on this Water Science Software Institute, which is the folks that sponsored our trip to come over here. We have a conceptualization award where we're thinking about what might a Water Science Software Institute be, and that national working group that I mentioned that's focusing on green stormwater infrastructure. The idea is that you actually combine software development with the research, and you have a working group that consists of both researchers and software developers. And we start out identifying what do people need to be able to do their research better, and in this case also to help with practice, and identifying barriers, designing some software that will help with that, implementing it, investigating and refining it, publishing it, and then starting around the loop again. And each time the community gets larger because everything is open source and you're sharing it. And so we want it to percolate out and share the software and that we're using and leverage other software. So, and what we're talking about while we're here is how do we do this internationally? And you know, if you're working in some of the same spaces, how can we amplify our efforts through this kind of structure? So this working group is focusing on urban green stormwater infrastructure at multiple scales, everything from spatial to temporal, short-term and long-term, to social. And we have 3 different research questions that we're focusing on. And the one we're looking at here in Australia that my student Sammy is working on is the 3rd one. So what are the trends in social and ecological resilience and green infrastructure installations in urban settings across 5 cities? And now we're starting to look in Australia as well, hoping to do Melbourne and Adelaide, but we'll see if we're able to get the data for both. And what factors are causing those trends? What locations and types of green or gray infrastructure would provide the greatest improvements in resilience? And we're measuring resilience from social, economic, environmental, and infrastructure perspectives, engineered infrastructure. So that work is just getting going, and this is what the working group will be doing, is creating some Software, we're focusing primarily on creating data maps that help us overlay. How do we get and find this data that we need? Setting up these workflows like I was talking about, and then sharing them amongst different researchers. So just to wrap up, big data and systems thinking, I think, can help a lot with these kinds of urban stormwater problems where we're doing some parts are data-driven, some are model-driven, and then we bring them together. Designing green infrastructure for benefits, looking at a larger system than we've done in the past. But to do that, we've got to do a better job of how we do the modeling, how we do the systems analysis and the informatics, and the tools to support these collaborations that we're doing more and more. And these are our funders and our collaborators. And I'll stop there and take any questions. Thank you very much.
So any questions for Barbara? While you're thinking of something, I'll come back to your first part of the presentation about the GAs, since I've got an interest in those. What sort of run times did you get for the operation? Because you're talking about 15-minute decisions, so you've got your GAs to run in a few minutes, is that right? Or?
It depends on which scale you're looking at. So the pilot scale is easy to do in 15 minutes. When we got to the larger scales, we're not down to 15 minutes yet, so we've got to keep working at it. Part of that was parallelization, because my student unfortunately wrote the code in MATLAB, and our MATLAB license is limited to 8 processors. So she wasn't able to parallelize it as much as she could have. So we can get a big reduction just from doing that pretty easily.
And MATLAB's pretty slow compared to, say, a program in C or something like that as well.
Yeah. So I think for the second and the larger scale systems, we probably could get it down to 15-minute solutions without a big problem. Now, if we wanted to do the entire system, that might be more of an issue. So there's still plenty of work to be done. What we haven't looked at is, some of the meta models, where you bring in a neural network or some other model to replace the hydraulic model and speed things up. We could probably gain a lot from that too. My poor student needed to graduate and move on. Yeah.
Other questions? Peter?
Could I raise a question? When you first started, you were talking about the Chicago tunnels and the implementation of grey infrastructure and the significant costs involved, and that led to the green infrastructure. But the scale at which green infrastructure is being implemented in Australia is the sort of micro scale. Do you have major green infrastructure projects that allow comparisons to do the sorts of things that have impact at the scale that you would work in Chicago?
Yeah, so the scale is a big question. Actually, here in Adelaide, you have larger scale green infrastructure than I've ever seen in terms of the rainwater harvesting that's being used to irrigate, some of the green spaces in town. It's fairly impressive, and I don't think anybody's thought at that kind of scale in the U.S. that I've seen yet. So for the city of Chicago, we don't have shortages of water. It's very rare when we have a drought. So our problem is more flooding, and the problem with the green infrastructure is it's going to handle the smaller storms. It's not going to really cut off the big storms. We're still going to have floods. So I think we're going to probably still need some gray infrastructure for the big storms. They probably don't have enough of that yet. But we have to model, when you bring in those reservoirs, how much benefit will we get? Can we fit more in this tunnel and reservoir system than we had before? So there's a lot of questions still. The scaling is big, and that's why the co-benefits are so important. We're just looking at, here's the different kinds of co-benefits you might get. There are some people trying to monetize that and say, how much is it worth for people to be healthier with green spaces? And if you're really going to get to the decision makers, that's probably a step that's going to have to happen. It's not going to happen in our project, but we have met some people trying to do that we could perhaps collaborate with. It tends to be more of a grassroots project. process. And this is where MWRD struggles because they know how to manage big infrastructure. They have engineers, they know how to run it well. You're talking about putting green spaces out in the city. They don't know how to do that. They don't know how to maintain it, so they have to talk to the park district, and they're talking about paying the park district to maintain the stuff because, you know, when they've got their own system, they're maintaining it, they know it's going to work well. If they're counting on all these people across the city, it's just a whole messy problem for them. So they would rather put in the gray infrastructure, but they're getting all this pressure to put in green infrastructure instead. So it's a very interesting time to see how this is all going to play out. There's a big push in the U.S. to do green infrastructure instead of gray, but is it going to swing back the other way or land somewhere in the middle remains to be seen.
Other questions? Yes.
You have the benefit of just one tree, in terms of...
One tree per yard. Yeah.
But it just seemed to be a large sort of, I guess, benefit.
Yeah, I thought it was a lot too. And that's why I had to go back to my colleague who wrote the model. And I said, is this really right? And he said, yeah, I think it is. But, one tree has a lot of roots, and I guess it makes a big difference in terms of how much water is actually draining off. They take up quite a lot. My class did a project with the International Arborists Society, which it turns out is headquartered in Champaign, where I live. And they told me that I think if you took away all the trees in the city of Chicago, they estimate that the runoff would increase 40% because the trees take up so much water. So I guess they do a lot. But, those were fairly preliminary results. So we got to go back and check them, make sure.
Other questions? Yes.
I'm just curious about the flood forecasting, the short-term flood forecasting sort of part of your presentation. I sort of got this idea in my mind about, infrastructure, and then what happens when there's some unknown that happens, some part of the infrastructure breaks or something that wasn't foreseen by these models. Is that...
Right, so the computers are not going to operate the infrastructure. The computer would make recommendations to the operator who would then look at everything else that was going on and decide whether the computer was right or wrong. You will always have the human operator there.
It's very hard for an operator to...
Well, the operator's operating with very little information right now. And it's really fascinating when we actually have a decision dashboard that we've created for them as well, where we took all their historical data and we brought it together so they could play videos and watch where the overflows were happening during storms. And they won't let me show it to the public because they're so scared to death of being sued again. But they look at this and they say, wow, because they had no idea what's going on in their system. They've never really looked at their data. And the way that they would do it, if there was a bad storm event, they would get some numbers, and write them down on a sheet of paper, and then they'd sit in a conference room, and I've seen the chalk drawings on the board as they try to figure out what happened in the system. They just don't have any clue. So I think this will help to have that information quickly available to them. Right now we're doing it offline, looking at historical information. But down the road, we expect that it'll go to a real-time system. But right now, their data infrastructure can't keep up with that. They're collecting information in real time, but they're not using it in real time. They go and they download it once a week and bring it in. So they want to see if it's worth putting that kind of infrastructure in.
Have you looked at, you used the 2-hour rainfall forecast,
Mm-hmm.
have you actually gone and looked at even just that data that's coming in, how accurate was the 2-hour rainfall forecast in terms of, like if you predicted you're going to get 10 millimetres an hour, did you actually get, over those 2 hours, did you actually get that, or did you get something different?
Well, in this case, this was offline using a historical storm, so we knew exactly what the rainfall was.
Yeah.
But you're right, that there's errors. The problem is that the rainfall forecast models don't give you error bounds.
Yeah.
If we knew the error bounds, then we could, give some error bounds and make suggestions that would be more robust. we could try to do that retroactively by looking at the errors in their forecasts and using that as some kind of error bounds, and then try to optimize to be more robust to those errors that could be there. But we haven't tried that yet.
In Adelaide, the times you get the worst events is when you get rainfall outside what the Bureau of Meteorology is actually predicting. So every time they predict 30 millimetres and you get 130 in.
Yeah, definitely. I have another student, another project where we're looking at drought forecasting, real-time drought forecasting in Texas, where they've had terrible droughts. And so my student, we're creating one of these web applications with web services and allowing the water allocation decision makers who every day have to make a decision about how much water people can withdraw during a drought, that they can run different scenarios on the model to see what might happen. So she's gone in, taken the historical data, and looked at how much runoff is the National Weather Service forecasting, and then how much error was there in the past on those forecasts, and then provide that as bounds, as a suggestion for different model scenarios that they could try out to improve the water allocation. And then we're going to do some optimization of that system to help them optimize what kinds of water allocations might be best. And we'll use error bounds for that. So it can be done retroactively, but it'd be another PhD to get that one done on this one.
On your, when you're looking at the green infrastructure, you talked about the social, economic, and environmental. And I guess, we try to do triple bottom line assessment here, but often with a lot of evaluation, the economics implicitly carries more weight. And I guess there are ways to try to put economic value on some of the environmental and health benefits, health effects, saving in hospital days, people's willingness to pay for the green infrastructure. Do you see that fitting within the framework?
Yeah, I think you could easily take these numbers and put them into a model that would have that economic impact very nicely. It's not scoped in our project, but I would love to collaborate on doing something like that.
Any other questions? Yes, Mark.
Quick question. One of the challenges in Adelaide or Australia with some grid infrastructure and stuff is the cost benefits are not it's not like an overseeing authority that has cost benefits are shared amongst different stakeholders.
Yeah, and sometimes the benefits are incurred by a different entity than the one that's paying for it.
Yes, that's right. So I'm wondering, in the US, is that a similar?
Yes.
And that's one of the big barriers to take up some of these things.
Huge problem.
You don't have that equity in terms of the, sort of thing. So is that a challenge in the US as well?
Absolutely. In Chicago, they were kind of smart, and they, the Metropolitan Water Reclamation District covers the whole metropolitan area, including downtown, but also a bunch of the suburbs. And they have a tax on everybody who lives there for their stormwater that pays for all of this. And so they can take that tax and use it to invest in green infrastructure to try to reduce, at least for the smaller storms, reduce some of the overflows that are happening through green infrastructure is where they're trying to go with it. And then they're also going to pay the park district to maintain it for them. And then they're trying to figure out, though, where do we put it? So they're trying to put it maybe in some schools where that green space will benefit the schools. But it's really complex because then you've got the city of Chicago involved as well. Turns out the city owns the sewer pipes down to a certain size, and then the MWRD takes over from there. And so for years, the two of them were pointing fingers at each other and saying, well, it's your problem. No, it's your problem. And they'd go back and forth. So the institutional barriers, Sammy and I were talking about this. We're hearing them here in Australia. We also hear them at home. And I think we need to start figuring out how to incorporate that into forecasting. So we're talking about maybe using agent-based kinds of models where you have agents making different decisions from different kinds of organizations as you're trying to forecast what would happen. But also, Sammy was thinking about maybe using some game theory to actually game the different people against each other and see what happens. So, yeah, I think it's very, very important for this in particular. I think some water systems are much more straightforward. One entity owns them, they take care of them, they incur the costs and the benefits. Green infrastructure is much more complicated.
Okay, well, I think we'll have to wind up on that note. And Barbara, we'd like to thank you for your very interesting and stimulating presentation. And it's nice to hear that we're not, what we're doing in Australia is also quite of interest to you. So
Absolutely.
we're getting something out of your brief visit to Adelaide. So I'd ask everyone to join me in thanking Barbara for her presentation.
And I also want to introduce my student, Sammy. Can you wave? He's here with me, and he's going to give a talk tomorrow at 4, right?
Yeah, 4 o'clock in S112.
Yeah, talking about some other work looking at sustainability indicators for cities where we're using text mining of newspaper reports to try and derive sustainability indicators. So, different kind of big data approach. Thanks.
Okay, thank you. That's all right. We actually recorded it on the civil engineering